So yeah, we're gonna start with the CCC 2018. We're gonna start with the junior 3. We're gonna skip the first 2 junior problems because they're very easy compared to the harder ones, and we want to talk about kind of the more challenging problems because they require algorithms to solve. So I'm gonna start with J3. Matthew, you can take it away.
Amazing. It's me. Wait a
Mhm.
second. I need to prep my screen. Okay, cool. I shall share my screen now. Yes, I will share 2 things, but I will share my screen first for this. So we're gonna first kind of read the problem, see what's going on, how and the specifications here. So I guess I'll read out the problem for
Could
you.
you provide a can you provide a link to the problem so then participants
Yes,
can read along?
I
Cool.
will. Amazing. Why am
Amazing.
I so bad at this?
Oh, Martin got it.
Oh, thanks, Martin.
Thanks,
Yeah, Martin has a link.
because I cannot find the chat box. I'm not good at using Zoom.
Echo brain.
Yes, I am very smart. Well,
Right.
anyway, so I'm gonna read our problem. So you decide to go on a very long trip on a very straight road. Along this road are 5 cities. As you travel, you record the distance between each pair of consecutive cities. Then you would like to calculate a distance table that indicates the distance between any 2 cities that you have encountered. And so we know that we have 4 distances between the first, second, and then as you continue, each less than 1,000. And then we want to make this table as shown here. So on the surface, this may seem a little difficult, but actually since this is a very simple problem with only 4 inputs, and we know every single time it's going to be 4 inputs with actually quite small specifications, the best way for this is actually a lot simpler than you think. The best way for this is actually just to hard code it, because that would be fastest, and you don't need to get too heavy into for loops or any type of loops, because for this problem it's just relatively simple to calculate the distances. So we're going to talk about this little document I made because I didn't have a lot of time to do other stuff. So here I wrote out specifications for any distance. We know it's from between 1 and 1,000. And I wrote down how we can think of any sort of distance. Say if we start from city 3, we can figure out what's the distances to each city by using this tables. And we can follow suit using this for not just city 3, but the first city, second, third, fourth, and fifth city. And this is basically the way you would want to do it on the DMOJ website for this problem. And I wrote a little bit about extending the problem where now say instead of 4 cities, you're n cities. You don't know how many cities there are. So you can't brute force it because brute forcing and hard coding require you to know how many cities there are. So this time for an extension problem, you're going to have to get more into for loops, calculate all the distances behind it and ahead of it using for loops that start from your index, say city 3, then moving backwards, and then another index starting from city 3 moving forwards. So that's an extension problem, but from the main problem, just basically just hard code it because that's the easiest way. So that's just J3 basically.
Thanks, Matthew, for that really great explanation. Well, now Matthew again is going to talk to us about sunflowers, which is CCC 2018 J4, and that was also the senior 2 problem.
Yes, I am here to talk about this problem, sunflowers. So Barbara has n different sunflowers, each with a unique height, order from smallest to largest, and records their heights for n consecutive days. Each day, all of her flowers grow taller than they were the day before. She records each of these measurements in a table, 1 row for each plant, with the first row recording the shortest sunflower's growth and the last row recording the tallest sunflower's growth. The leftmost column is the first measurement for each sunflower, and the rightmost column is the last measurement for each sunflower. If a sunflower is smaller than another when initially planted, it will always remain smaller for every measurement. However, or unfortunately, her children have altered measurements by rotating her table by multiple 90 degrees. Your job is to help Barbara determine her original data. So we know, and we have a specification of this n, how many consecutive days, is from 2 to 100. So we can read the problem. We realize, so we're dealing with a 2D array. We have a 2D grid of these numbers that we want to keep rotating until we can find it and make sure this is like this in an increasing order. And something that may be a little unclear from before is unclear, or how should I say, not should be unclear, but or is something you should realize pretty quickly is it doesn't really matter which way we turn it, whether it's clockwise or counterclockwise, because when you think about it, turning it 270 degrees clockwise is the same as turning it 90 degrees counterclockwise. So right now, our main objective here is to find how we can rotate a 2D grid by 90 degrees. And there are numerous ways to do this, but there is actually a very sorry, I got distracted a little bit. There's a very elegant way to do this, which involves some math and some visualization, because you're going to have to do some drawing to figure this out. But there is a very elegant way to do an almost an in-place rotation of a grid. However, this way, the way it's not completely in place, because you're going to have to transfer the original grid to a new position, but it's very elegant. So we
Wait,
can,
what do you mean by elegant?
elegant meaning it's actually, the way you would do this is actually pretty, it's not that hard or not that hard, it's pretty simple, and it wouldn't involve a lot of coding. You wouldn't need to write like 100 lines to do this. It would be pretty short. And I'm gonna, I guess for this one, since it's a little hard to explain properly, I guess I'll show you my solution of how I did it from a long time ago. This is a long time ago, which is a couple of years ago. So it may look a little rough on the edges. Yes, see, this doesn't need 100 lines of code, but when I doing it, I added an extra code, and I didn't know how to use functions back then, so it looks pretty rough. But see, you can see here that the main point of contention I want to talk about is about this line right here. This is the most important part, and this is how you rotate a grid into from 90 degrees clockwise. You would have, so for any position, you would move, this is how you would do it. And this may seem a little complicated, and I can't really get exact math right now, because it's pretty, well, it's not really, it will really take too much time, and I just don't really want to explain it right now because it's just way too complicated. But this is how I do it, and I'm sorry if I seem a little scattered or not really explaining this properly, because recently I had a lot of things to deal with. But later on, I'll write up a math explanation on why this works. But for now, all you really need to know is this is how you would do it.
You want me to explain it a bit?
Yeah, sorry. I had a
No,
lot
it's
of
fine. It's fine. I'll just explain it. So essentially, Matthew's code is very smart, because what he's doing is that he's trying to find a mapping rule. Now, you might ask, what is a mapping rule? Well, a mapping rule is actually really simple. All that is that you're taking some part of the array, like some element of the array, and you're mapping it to some other element. If you've ever done transformations in grade 10 or 11 or 12, you know that when I want to transform some function, I want to maybe shift it or stretch it to some value. And this is the same thing, right? But instead, we're not dealing with functions, we're dealing with arrays. We're dealing with two-dimensional arrays. As you can see, the rotated array is a two-dimensional array with many elements, and we want to move every element to a specific another element in the table shifted grid. So that means we shift this grid into the other one, and the way we do it is we kind of use a bit of math. And the math behind it is actually really simple, right? All you do is that you take, let's say, the first element, which is 0, 0, and let's say you're shifting it 90 degrees, you're going to shift it to 0, 3. And you're going to keep shifting every index and then find a pattern. So for example, a 90-degree rotation, you're going to realize that from any point x, y, you're going to shift it to a point y, comma, n minus 1 minus x. And that's because you shift it to the right. The y value doesn't move because you're shifting 90 degrees, if you think about it in your head, but you're only moving, you're flipping the indexes, and the x changes because you're rotating it down. So you essentially do every 90-degree rotation, write it on paper, and then look at the pattern you find, right? Because for these problems, there usually isn't too big of a trick. The gist of doing this is just to write it all down and then understand the problem in your head, so you know how the intuition behind the problem works, right? So just like what Matthew did during the contest is that he found this mapping rule by writing down everything, and then it's really simple because you loop through every element in the array and you use that mapping rule, kind of how you map every function to another function, if that makes sense.
Yeah, Jerry explained it pretty elegantly, and like I said before, I'll later on draw up a diagram and write it down. So for people who have hard time just like understanding without a visualization, I'll draw a diagram so you can like help better understand how the process really works. But as you see, it's very short and it doesn't need a lot of code. So sorry, I just had a hard week. I just didn't have a lot of time to do this, and I'm really sorry about this.
It's fine. All right, let's keep on going. Next thing we're going to do is Voronoi Villages, which is this year's S1, and that's going to be, Jake's going to take us through that. So take it away, Jake.
Hello. Here's the question link. Am I sharing my screen? No, I'm not.
No, you're not. Yeah.
Wait, that's not my screen. That's my screen. Okay.
Accidentally shares his Twitch channel.
Hey guys, I troll like no, I'm kidding. That's the wrong document. That's my work. That's not the right one. Okay. Voronoi villages. In the country of Voronoi, there are N villages located at distinct points on a straight road. Each of these villages will be represented by an integer along this road. Each village defines its neighborhood as all points along the road, which are closer to it than any other village. A point which is equally close to two distinct villages, A and B, is in the neighborhood of A and also in the neighborhood of B. In each neighborhood has a size which is the difference between the minimum leftmost point in its neighborhood and the maximum rightmost point in its neighborhood. The neighborhoods of the leftmost and rightmost villages are defined to be of infinite size, while all other neighborhoods are finite in size. Finite in size, there's like multiple ways to pronounce that. Determine the smallest size of any neighborhood with exactly one digit after the decimal point. Right, so you have like, you have this test case, which you have n, which is the number of inputs, and the points in which the villages are on, technically speaking. And so like, you'll see that 3.0 is taken from the fact that the smallest village is 3 in size, right? The neighborhood around 15 goes 1 up, 1 unit up to 16. It's equally as close, so that's 1. And the neighborhood around 10 is 5.5. So 3 units to the wait. Oh. Wait, no, it's because it goes 0.5 to the right, which is shared by 16, and 2.5 to the left, which is shared by the 10. And then they'll give you your answer of 3.0. And so basically, in this question, to find points between here and here, you take your eye position of this, and you find the leftmost bound and the rightmost bound. So pretend in this test case you have 15, 10, 15, 16. So you do 15, no, you do 16 minus 15, right? And that'll give you the difference between those two, and then you divide it by 2, and then you'll get whatever you'll get your bound. My bad. I'm tripping over my words. So for the leftmost bound, you'll have 15 minus 10, right? That'll give you 5 divided by 2, and then you'll get your 2.5 bound. You add them together, and then you'll get 3.0. I hope this isn't absolutely horrible and messy, but probably is, but I hope you understand. And so you do that in code with that's not the right one, with this, right? You find vi plus 1, which is 16, minus vi, which is 15 in this particular case, and then you take it, you get your rightmost difference, and then you'll get divided by 2, and then you add it with your leftmost difference, which is vi minus vi minus 1, vi, which is 15, vi minus 1, which is 10, and then you divide that by 2, you add it to you add L and R together, and if it's smaller than your smallest, then you'll get your answer. I think I'm also doing cyclic shifts, but that's not this year's. So we're going on to next year's. Jerry, you wanna?
Can you stop sharing your screen first? I can't share my screen when you're sharing.
How do I stop sharing? Oh wait, no, I found the button was the button was hidden. Okay, it was on the other screen. It shouldn't be there.
So thanks, Jake, for that problem. We're actually going to move on to this same year's J5, which is the last problem we're going to do from this year, and then after that we're going to move to the CCC 20. But for now, I'm going to quickly share my screen, and then we can talk about this. So how do I share my screen again? I'm very smart, as you can see. All right. Yeah, I shared my screen. All right, so first of all, let's look at this problem, and we're going to analyze it the way that I would do it on a contest. Now, first of all, let me preface this by saying that this is not indicative of what an actual Junior 5 looks like on the CCC 21, because usually on the CCC in previous years, they are much easier than the CCC in harder years. That's especially true because as they get harder, people, people are just getting smarter. There's no non-blunt way to say it. So you just really have to practice a lot of these past problems, and even like present problems. Like if you go to DMOJ, there are lots of contests here that you can, not these ones. Like there are contests here that you can try, or even just past contests that you can do just to improve your CCC skills. But other than that, we're gonna now look at this problem. So let's first look at the problem. We're going to read through the problem once, and then the second time we read it through, we're going to understand what it's asking of us. So you can just read it through once, maybe while I'm kind of talking about random stuff, and then I'll read it again, and then I'll show you how to look for the important things in the problem. I trust that you read it once, so I'm just going to read it again. So first of all, there's a genre of fiction called Choose Your Own Adventure books. These books allow the reader to make choices for the characters which alter the outcome of the story. This is completely garbage. Let me just start by saying that that's just absolute garbage. A huge part of a CCC problem is just absolute garbage. Just when you look through a problem, you can actually see that. Like, it just, I don't know why they add a bunch of flavor text to the problem, but it's just absolute garbage. So let's just keep going. For example, after reading the first page of a book, the reader may be asked to make a choice, such as do you pick a rock? Reader answers yes, they are directed to continue reading on page 47. If they choose no, they are directed to continue to reading on page 18. Okay, this actually is important because let's say, let's say you're at page 10 and you can possibly go to page 18 or page 47, right? Depending on what the user chooses. And then some pages do not have any choices and thus are the ending pages. Now, this is important. They're ending pages of the book, right? Maybe let's say from 47, you go to 82 and that's it. That's the end of the book, right? Like some of them are, the hero finds a leftover sandwich, which sucks. Maybe this one sucks and maybe this one is really good, right? Like this is just an example of a book, right? Like maybe this one's really good, this one sucks. And then you're the editor of one of these books and you must examine 2 features of the Choose Your Own Adventure book, right? So now this is the important part. This is the important part because now it's going to tell you what you need to do. This is garbage. This is kind of useful for a sample, but this is the useful part. This is the very useful part. First of all, you need to ensure that every page can be reached, which means that let's say there's a page 19, which can never be reached by anything, then you can't reach every page. The other one is that you find the shortest path so that readers will know what the shortest amount of time they need to finish one version of the story. Okay, so we need to do 2 things. We need to ensure that every page can be reached and we need to find the shortest path. Good. All right, so that's the information that we took from the problem. Now that we understand the problem precisely and really well, we're going to walk through a sample with you. I'm going to show you, I don't know why nobody used this. I don't know why nobody used this document. We're supposed to use it, but since nobody's using it, I'm not going to use it either, and I'm going to be Jake and use Paint.
That's Paint gang.
So let's do a sample case,
okay.
right? Let's do a sample case. So let's say that, let's do a really simple book. Okay, that was the wrong screen. Let me just, nobody needs to see this.
Like mode Discord.
Yes,
Like
that's the
mode
exact chat.
Discord.
Yes.
Discord light theme. I.
Yeah, so
Gross.
let's look at a simple sample case. Let's say that, let's just go to our previous example. So from 10, we're going to go to 18, and we can also go to 47, and I'm just going to make up one more. Maybe from 47, we can go to 82. Notice that there we can go from, or let me just draw arrows, right? From 10, you can go to 18, and then from 10, you can also, let's say 10 is the starting page, or 10 is the starting page, you can go to 42 or 81. And this is even without even looking at the question. I just look at the question, I kind of formulate this picture in my mind, and I say that, okay, so first of all, let's say there's also 92, and that's another page. First of all, I'm going to formulate that, can we reach everything? No, because 92 cannot be reached. So the answer to the first question is no. And the answer to the second question is, can we find a shortest path? Well, yes, because the shortest path is just 1, because if we start at 92, we can never even get anywhere, so just 1, right? So basically, or let's say there's no 92. What about now? Well, now we can reach every page. So the answer is yes. And the question asked is, what is the shortest path? Well, now it's 2 because from 10 we can go to 18, right? So that's going to be a sample case. And then we're going to go back to this. But this is kind of like you're formulating a question, the problem in your head. Now what you do is you go to the input specification. This is important. And then the output. You read it once and then you read it again. Let's go to sample input. So N is less than 10,000, M is less than 10,000. We're going to skip these for now. I'm not going to mention subtasks yet. If you learn about Java, CP, Python, you're going to know what subtasks are. Don't worry about them if you don't. I'm going to explain them. And then these are some other available marks. We're going to talk about subtasks again later. But let's first look at the output specification. So we need to know Y or N if it's reachable or not. And we also need to give a positive integer K, which is the shortest path. Okay. So now that we know what we need to give, let's look at now the sample input. The sample input is kind of your first hint towards solving the problem. If you don't understand the sample input, you can never do the problem. You have to understand this first. So let's look at a sample input, and we have 2, 2. So that means this means that from 1, right? So this tells you that N is equal to 3. So there's three pages, right? And then what it also tells you is that from page 1, you can go to 2 pages. You can go to 2 or 3, right? So from 1, you can go to 2 or 3. And from 2, it's 0, which means you can't go to anything. which means it's an ending page, and 3 is an ending page. Notice the important parts here. You should always begin the book on page 1. You always begin on page 1. This is important because this is going to be used later. Always start the book on page 1, right? And then the other important thing is we notice that there will always be at least one ending page. This is important because if there's no ending page, something might happen. You can think about what might happen now. I'm going to explain it later. Just keep it in your mind. So for this one, let's try to solve it, right, without a computer. So for this one, it's yes, we can reach every page because 1, 2, 3 can be reached. And also the shortest path is 2. Let's see if we're right. We're right. Okay. So this means that we understand the problem perfectly. Now we're going to start formulating a solution. Let's first start with a naive case, right? Let's first start with a bigger case and see how we can solve it naively, right? So just by naively, I mean normally, like without really thinking about any algorithm, because this is the first way you should approach a problem. If you start out by thinking of a very complex algorithm, maybe you can, but probably you're not going to, and you're going to spend a lot of time doing nothing, right? So think of a brute force algorithm. Let's see, what can I do? Well, what if I store everything? Well, let's say that 1 is connected to 2 and 3. I'm going to store that in an array, right? So this is going to be 2 and 3. And for 2, since it's stored in nothing, my 2 array is going to be empty. And so is my 3 array. Or maybe let's put something like -1, which means that it's empty, right? This is what I'm thinking. Remember, this is just a brute force. This is a random solution. I'm thinking of it on the spot. And then we notice that 2 and 3. What do I see about this? Well, from 1, I can go to 2. This is 1, 2, 3. From 1, I can loop to 2. And from 1, I can loop to 3. And that can solve the problem. So the simplest way to do it is just loop from every problem. Okay? So that is, without even doing the question, there you find a way that you might be able to solve the question. Right? I haven't even thought of an algorithm yet. But the next thing we need to do is think of this, right? First of all, how much space does it take? Well, it takes a lot of space because for every connection, we have to store it in a gigantic array, right? So we have like a lot of arrays here, and it also takes really long to loop because from every point, we need to loop to a lot of points. And do we know how to loop in this way? Not really, right? Not really. Maybe we do, but not really. So now we're going to think, how can we improve on the solution to actually loop? And this is where our recursive intuition comes up. This solution probably needs recursion. I said this like just out of my head because I already know this, but what if you don't know this? How do you know that this is recursion? It's actually really simple because think of a bigger case. If I have a bigger case and I need to have a bigger array, doesn't that mean that from this one, I need to go to this one and then go down, right? Like every step leads to another sequential step, which means that I need to use recursion. Does everybody understand that? If you don't, put in the chat and I can explain again. The intuition behind it is that you need to use recursion because each step is sequentially constructed from the previous one, which is why we need to use recursion, right? And then we need our recursive intuition. That includes our base case, inductive step, and inductive hypothesis. If you didn't take the recursion class, that's completely fine. Basically, what that means is that we need a starting point and somewhere to go to from each eventual step, right? So our base case is going to be 1 because our book always starts from 1. See, remember I told you that would be important. And what is the end? Well, the end, if we know that we completed it, is what is the end? Do you want to put in the chat? What is the end? 2, 5, 2, 5, 3, 4, 5. That is not the end. The end is when we end, when we have an ending page, right? That's when we end. Martin is technically right because any page can be an ending page, but I was kind of looking for the answer that the ending was any ending page as possible, right? And now we need to think of our recursive step. And recursive step means to go to every next page, go to all pages connected to this page. Now, if we look at this recursive step, we see that it works because let's say from 1, we can go to 2. And from 1, we can go to 3. And then from 2, because there's nothing connected to it, we're done because we reach an ending page. And from 3, we're done and because we reach an ending page. And then how do we give the shortest path? Well, that's actually pretty simple. Because from here, we can kind of just say, oh, let's look at this 2, right? Like, let's look at this value. if we count every time we do this, so let's say this is count 1 and this is count 2 and this is count 1, this is count 2, we can kind of find the smallest count once we reach the end. And here we're going to find smallest count, right? And that's our algorithm. And then let's say another question is, how do we know if we reached every one? So if we reached every one, what if I make another array and just check if every element has been reached? So let's say there's 6 pages. I'm going to check it off if every page has been reached. And at the end, I'm going to say, let's say, oh, this page hasn't been reached. Well, that doesn't work. See, I transform the problem from a completely unknown brute force solution to a recursive solution that solves the problem partially. I say partially because we don't know if it can pass or not. We don't know how fast it is. Well, first of all, let's look at how fast it is. Let's look at how fast it is. Let's look at how fast it is, right? So essentially, now that we have a solution, before we can actually use it, we need to understand how this case works on any test case, right? So let's, again, now we're going to go back to the subtask, and we're going to see that subtask 1, for 4 available 15 marks, these numbers are all small, which is good because our solution is not that fast. For an additional 3 of the available 15 marks, the book is guaranteed to have no cycles, which means that you cannot go from A to B and then back to A. That's good. But then what if we think about it? What if we have cycles, right? This is going to be devastating. This is going to be devastating. Why? Why? Because if you think about it, if I start from some, I don't know what's going on. All right, let me just cut this. All right, if I start from some value A and I go to some value B and I go back to some value A, what is that? What is that called? That is called infinite recursion, right? Because I'm going from some value and I'm going back to the same value. That's devastating because what happens is that I'm going to keep going to B and I'm going to go back to A and I'm going to go to B and I'm going to go to A and I'm just going to keep on going forever. My program is never going to stop and your program is just going to crash, right? We don't really want that because we don't want our program to crash. This is not ideal for us. We don't want this. How do we make this ideal then? Well, we need a way to keep track of cycles. And this comes to our other recursive property, which is, remember when we looked, when we had an array for when each element was reached? Well, I can just do that again. But instead of doing that, I'm going to keep track of everything that's been gone to. If I go to this one, I'm never going back to A because A has already been reached. And that's how I deal with that. And with that, I can actually pass almost all the subtasks. The last optimization is, you notice that this is very slow. Very, very slow. I'm going to talk about time complexity. If you don't understand it, you can go back to read the lesson and I will also explain it. What is the time complexity of the algorithm? First of all, only now do you do the time complexity, because with this algorithm, it should pass all the cases. If the cases are small enough, it should pass. Only here, when you have a good algorithm that should pass all the cases, if the cases are small enough, this is only when you start analyzing time complexity. You don't analyze it when you have a really bad solution, right? You analyze it when you have an okay solution and you see if it's a perfect one. And we see that it's not. It's really not. And the problem with the reason that it's not is, if we go back to the problem, n and m can be up to 10 to the 4, right? And if we look at it, what if we have 10 to the 4, n equals to 10 to the 4? That means from each node, we're going to have to recursion to multiple different nodes. There's one way you can leave this, is if we take one node, like if we've gone to this node, we never come back to it, but that will just make the problem wrong. So we have to go down every path. And if we notice that they're 10 to the 4, so there are most 10 to the 4 paths, and each of the paths take a certain amount of time to traverse, right? Because the thing you see is that, let's say from 1, I can go to 2, I can go to 4, but then from 1, I can also go to 3 and go to 4, right? That's just going to take a lot of work because I'm going to 4 twice. And what if I go to 1 and I go to 2 and I go to 3 and I go to 4? With 4 nodes, I already have these so many different paths. Each path can multiply it exponentially. So I have like 2 to the 10 to the 4 maybe different tasks. Now this is big O time. Again, we realize that this is exponential because this isn't exponential. This is like 10 to the 4. Let me actually calculate it. So from each step, you can have in most n nodes, and you have n steps, right? So you have n to the n. So it's incredibly big, right? So you have because from each node, you can go to as many steps you want. You can have at most n nodes at every step. And because you have a total of n to the 4, you can have like exponential form of nodes. Right? That's the overall time complexity. You see that this is really big. This is way too big to do it. I need to find a way to make it easier for myself. And this is when we think of it. If you don't know what this time complexity means, this basically means that it's exponential, which means that they increase much faster, because if you think about it, they branch out, right? Each of these branch out, which gives you a asymptotic notation of 2 to the n. Asymptotic means that it can be c times 2 to the n. It can be some constant, but the important factor is the asymptotic factor, because if you see something like a normal one runs like this, 2 to the n runs like that. This is 2 to the n, and this is n. We can't have this, right? This is like really fast. If you try to run this algorithm, it'll crash in 3 seconds. So we can't do this. What do we do? Well, let's find one more way to do this problem, which requires something called graph theory. Don't worry if you didn't learn this. We actually took this up in CCC Python. But essentially what this means is that we're going to model the problem using a series of circles. And these circles represent where I'm going to from each node. Right, so if I'm going to this node, I'm going to take a circle and then go to the next node like this. So for example, this is going to be one possible pathing. And this is going to be, let's say I'm doing this, right? And these circles should have direction, which I'm going to do that, right? And let's say this is 1, this is 10, this is 18, and this is 42. And notice that from every node, I can represent this problem. I can transform it into a graph, because I can, from each node 1, I can traverse it to get to the ending page. And that's how you know that it's a graphical problem. But you might think, what can I do with this? This doesn't help me at all, right? This is all really slow, but it's actually not. It's really, really not. And the intuition behind the fact that it's not is that I can now traverse the entire graph, right? And this is going to be something called BFS. Don't worry if you don't know what this is. Essentially, this is glorified recursion. It is called BFS because we want to be fancy about it, but it's really just recursion. But there are two modifications to the solution we're doing. First of all, we notice that there are 2 paths to reach 42. Which one is shorter? 1, 10, 42, which means that we're actually not going to go this path, because we're going to go to 42 and realize that 1, 8, 10, 18, 42 is too slow to reach it. It's kind of like if multiple people are going to the same location, but one person is traveling around the world and the other person is traveling to his neighbor. We're going to tell that person who's traveling around the world to probably not go that way, right? That's way too slow. And the problem is that in a computer, the person that's traveling around the world is also going to take up time. But we don't want them to, right? Like, why would you want someone to travel all around the world when you can just travel to your neighbor? Right? Like, it doesn't make sense, and it just spends so much time. So instead, we're going to take the path that's shortest. And let's look at an algorithm of how this works. Okay, but for this, I'm going to draw a few more circles. I'm not going to write anything in. I'm just going to show you how BFS works normally. All right, I'm just going to do this. This is the Bruce way of doing the problem. And then I'm going to connect these lines using arrows. These arrows suck. All right, so just using arrows like this. Arrows, 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 arrows. This arrow sucks. Arrows, arrows, and arrows. All right, so let's look at this problem, and we're going to see how we can do it. So from this point, we're going to see that the length is 0. We're going to have 2 arrays. We're going to have a distance array. We're going to actually improve it by having 2 different arrays. We're going to have a distance array and a visited array. First, we're going to go to here and say the distance is 0 and the visited is 1 because we have visited. Once we visited a node, we're never going to come back. And also, we're going to have what is called a queue. Look, everything that you learned is coming back. We use STL data structures, we use arrays, and we use graph theory, which uses recursion, right? We're using all of these things to help us. And we're going to go here, and this is going to be the distance is 1, right? Because from 0, I'm going to recursion down to every node connected to it. 1. This should actually be pointing this way because nothing can point away to 1. And this is also pointing this way, right? And then when we see that this becomes 2, this becomes 3, and it ends. This becomes 2, this becomes 3, and it ends. And then this becomes from 3. Let me just pretend this thing doesn't exist. Let's pretend this thing doesn't exist. And then from here, let's pretend this thing also doesn't exist. And then from here, we have 3. And then from here, let's say this is pointing that way, 4. And from here, 5. So now we have the distance from everything. And the distance to any ending page, the shortest distance, is going to be the shortest distance of every ending page. So every ending page. And we notice that that value is 3. So that means that our answer is 3. And can we go to every node? No, because if we don't have a because if one node is not visited, it's not going to work. It's just not going to work. And this is going to be not visited, so the answer is no and 3. See how easy that was? That was the entire problem. We transformed the problem into a graph theory problem and it becomes really easy. Now, for those of you who are more experienced, I'm going to do a really, really fast optimization in 2 seconds, which is we don't need a visited array. Why? Because if a node if we set all the nodes have a distance of -1, that means that if the node is never traversed, the value of that node will never change, so it's always going to be -1. And then we just loop through the distance array and see if there's any node that has -1 on it. If it has -1, that means it wasn't visited, and we can write n. Otherwise, we write y, and then we perform the same BFS. The BFS is very simple. The implementation is essentially go from every node and recursion down. So for int u, int v in u, right? So every node v in u, we're going to recursion to that node in v. And what you're going to use is something called an adjacency list or an array. You can actually store all these relations in an array, like 1, 2, 1, 3, 1, 3, and then we can also store stuff like 2, 3. But it's actually not needed because we can actually use what's called an adjacency list, which is just storing every connection of every node. This is also similar to what is a linked list. We talked about this, I think you guys talked about it in CP Java when you mentioned a linked list, and we also talked about it in STL data structures. But essentially, you take every node that is connected to it, and then you just make an adjacency list. If you need help with the implementation, feel free to ask, and if I think you understand the algorithm, I'll help you with the implementation. That is all for this problem. As you can see, this was much harder than the other previous ones because it requires a lot more thinking. But if you can get this, you're going to get CCC honor roll, which is very, very, very good. That is incredibly great if you can actually get this problem. But yeah. Apologies if that was long. But again, the problem was very long because it required a lot of intuition to solve. And it required a new concept, which is going to be very good for your CCC journey. And yeah. That's it. So now we're going to be moving on to the CCC 2020.
2020.
Yeah, so just going to start with Ryan showing us how to do J3 art so I can take a break from talking.
Very excellent explanation, Jerry.
Thank you.
Okay, so let's talk about art. And you might think CCC has nothing to do with art, but they make some very interesting problems. Okay, so Mahima has been experimenting with a new style of art. She stands in front of a canvas and using her brush, flips drops of paint onto the canvas. When she thinks she has created a masterpiece, she uses her 3D printer to print a frame surrounding the canvas. Your job is to help Mahima by determining the coordinates of the smallest possible rectangular frame, such as each drop of paint lies inside the frame. Points on the frame are not considered inside the frame. Okay, so this one is just to give you some context for the problem. You're not really going to use this afterwards, but let's look at the input specification. So it'll tell you the numbers of drops of paint, and it'll give you all the coordinates of all the points. So here we know that there's 5 droplets, and they're at these coordinates, x and y, on a plane. So they even gave you a diagram, which is really cool. If they don't give you a diagram, draw it out. Like, it's the best way to visualize things, right? So we do have these 5 points, and you see that they have drawn a frame around it, right? You're trying to make the smallest possible rectangular frame that goes around all of the points. So let's go take a look at how we can approach this problem, and I'll share my screen of my OneNote. All right, so this is what I did. I just drew an x and y coordinate around it so that you know like where the axes, right? And the first thing you want to do is understand the problem. So if it's asking you to minimize the rectangle, you're thinking about minimizing the area of the rectangle, right? And does anyone remember what's the formula for the area of a rectangle? Just put it in the chat so I know that you guys are listening.
Length times width.
Yeah, length times width. Awesome. So we've got, I'll just call it height and width because it's easier on an XY plane. So we want to minimize the area of a rectangle, right? What are two ways we can minimize the area of the rectangle? Well, we have height, we have width. So if we want to minimize the area of the rectangle, we want to minimize height and we want to minimize width. So let's look at the two different axes and see how we can minimize these two dimensions. So I drew a number line, right? And I just included the x coordinate of every single point. So if you see something that's really complicated like this, you want to break it down into like its separate dimensions, right? Break them down into a simpler problem. So this is the x-axis, and you have 24, 34, 42, 44, and 64, and I just took it from the points. So we're looking at where the left side of the rectangle can be and where the right side of the rectangle can be, right? So if I'm trying to minimize the difference between these 2 points, between the left side and the right side, I want to move the left side as close to the right side as possible, right? Without excluding a point. I want to move this to the right as most as possible. Well, can I move it past 24? No, I can't. I'm going to exclude this point, right? This point is going to be outside my frame if my left side of the frame is excluding the point, right? So it can't be on 24 because the problem stated that if it's on the frame, then it's not going to be inside the picture, right? So it's going to be at 23. 23 is the rightmost that we can go without excluding a point. And what about the right side? Well, we want to move the right side as close to the left as possible because we want to make the left side and the right side as close as possible to minimize the width. So what can we do? Well, we're going to try moving it leftwards until we hit a point, right? Well, can I move it past 64? No, I can't. I'm going to exclude the point that has 64 as the x coordinate. So the leftmost that I can move the right side is going to be 65. So now we know that the left side is going to be 23 and the right side is going to be 65, right? And this is the smallest that it can get while including all of the points. So now we know that, let me see if I can draw some shapes. Now that we know that the left side of the rectangle is going to be at, this side of the rectangle is going to be at 23, right? And we know that this side of the rectangle, can't draw. This side of the rectangle is going to be at 65, right? Awesome, we already figured out 2 dimensions. Let's look at the other dimension, right? Let's look at the y side. So now I just took the y coordinate of all the other points and I sorted them, right? Well, I'm trying to move the top one as close to the bottom as possible. So I move it here, right, which is 79. And I want to move this bottom line as close to the top as possible, which is 9, because if I do 10, I'm going to exclude this point. I have 9 here. Well, now I know where the top line and the bottom line is. So let's draw that onto . Awesome. If only I can draw. Okay, that's not perfect, but we know that this side is y equals y equals 79, right? And this part is going to be y equals 9. And this line was x equals 65. And this line was x equals 23. Well, then what did the problem ask us? Well, they wanted to know what was the bottom left and the top right. So what do we do? Well, this is just 23 and 9 because it's the left side and the bottom, right? So it's at 23 and 9. And here, what's the top right corner? Well, it's the top side of the rectangle and the right side of the rectangle. So that would be 65 and 79. So you see that there's been a pattern here. The bottom left corner is just the minimum x minus 1 and a minimum y minus 1. Because -1 because it can't include the point, right? And the top side is maximum x plus 1 and maximum y plus 1, right? So you just loop through all of the coordinates, find out what's the max x coordinate, what's the minimum x coordinate, and that'll give you the x coordinates of the top right and the bottom left. And then you loop through the points and you try to find what's the maximum y coordinate of all the points and what's the minimum y coordinate of the points. And then that'll determine your y coordinate for top right and bottom left. So that's all you needed to do. You only needed like a simple for loop. But then you needed to understand the concept, which is you're trying to minimize that rectangle, right? So if you want to do pseudocode, then it's just you just loop through all the points, right? Like, what was the input, like n? And then every single time you read like a x, right? And then you read a y. Well, then we can do minimum x equals math.min, like min x and x, right? So you just find what's the minimum and the maximum x and y, and then you just output that. And that would just be your answer. So it's relatively straightforward.
Thanks, Ryan, for that great explanation. I should turn on. Yeah, thanks, Ryan, for that great explanation. Oh, hi, Albert.
Hey, how's it going?
Good, good. We're just on CCC 20 now, working our way through them. The next one is going to be J4, cyclic
Yes.
shifts by Jake.
Presented by me again because
Yeah.
I'm doing it.
Anyway, out of the execs here, who wants to be the host? Because I'm leaving. Okay.
Okay.
Wait, Eddie, you can be host. All right.
Yes.
Bye, guys.
Okay, goodbye,
Bye.
Albert.
Bye,
Albert,
Albert.
Live-Solve, rule of 3.
Rule
Alright.
of 3 is such a joke. Okay, so cyclic shifts. First, read the question. Thuck likes finding cyclic shifts of strings. A cyclic shift of a string is obtained by moving characters from the beginning of the string to the end of the string. We also consider a string to be a cyclic shift of itself. For example, the cyclic shifts of ABCD are ABCD, BCD, EA, which you just move the A to the back. You have CDEAB, you move the B to the back there. You're just like shifting the word, you're just shifting the first letter to the back every time through these iterations, right? Given some text T and a string S, determine if T contains a cyclic shift of S. So I did this question using brute force and it accepted it. I don't think there's any huge test cases. So the input will consist of exactly 2 lines containing containing only uppercase letters. The first line will be the text T, and the second line will be the string S. For each line will contain at most 1,000 characters. For 6 of the 15 available marks, a subtask, S will be exactly 3 characters in length. And the output specification, output yes if the text T contains a cyclic shift of the string S, otherwise output no. So basically all this question asking you to do is, here's my string, right? You'll have like this, right? Now, tell me if like there is a cyclic shift of, let's see, a OHA in this random string, right? And so you'd be able to instantly tell that, yes, there is, right? Because you have HAO, you shift the O one back, and then you'll have OHA, right? And within their first example, they have the their first string contains CDEAB, which is a cyclic shift of their second string ABCD, right? And so basically to solve this question, you're going to just have to pretend like all these O's are like random letters, right? You shift the string as so. You take away the first. You take away the first letter, and then you move it to the back. My MS Paint skills are amazing. And then that letter will be there, and then you check the string again, right? And then you just keep on doing that. X this one, move this one here, and then
Is
if you
that
still
the
don't-
Amazon logo?
Yes,
How'd
that's
you
fake
know?
Amazon.
Rip off Amazon.
Jeff Bezos renamed his company to O.
Yes. You just keep moving the O's back. This is a very poorly drawn Amazon logo. And then you just check the string again for a cyclic shift of whatever string was inputted. And so we can do this with code like this. You have a string substring, which is I and I plus str2.length, which is basically just your second input. My variable names were not very
As you
good.
can see, str2.length.
Yes.
Yes. Very.
So
totally
basically,
not
this is
confusing.
just finding the substring. Then I put another 4 here to check if it contains a cyclic shift of the substring, which is this just shifts the substring a little, and then wait, no, not a little. It just takes the first. What am I saying? It takes the first character and moves it to the end, and then it loops again to check if the string is equal to the substring that I got, right? And then that's how you solve this one, basically. Then you output yes or no, and then you're done. And then I think it's Jerry's turn again to do escape room.
Actually, sure. I'll do escape room first, and then surmising spinner speed. Sure, it's fine. All right.
Wait,
Thank
what?
you,
Did I
Jake,
miss
for
something?
that. Nope,
You missed a problem.
it's okay. It's okay. I'll do it first anyways because I have to go in like 10 in
Okay.
a few minutes. I'm gonna explain this quicker than the last one. The reason I'm able to is because I established what graph theory is in the previous problem, so this problem should be much easier. Give me 1 second, and then I will share my screen in like 30 seconds. Okay, so we're next one we're gonna talk about is CCC'20's S2, which is escape room, and I will share my screen and we will look through the problem together. Also, if you didn't see in the chat, Ryan actually posted a very big brain solution to cyclic shifts, which is using something called string builder, which is only for Java, but if you're a Java main, you can try that. But if you're not a Java main, don't worry about it. All right, so for escape room, because I took you through the problem completely once and you saw my entire thought process for doing CCC'18 J3, and also because this question, J5, and also because this J5 or S2 is much harder, we're just going to do a solution sketch, and I might even show you how to do escape room hard. But basically, let's first look at this question. So basically, I'm going to summarize the question, which is you're given a 2D grid. And what you want to do is that you want to go from one side of that 2D grid to the other side of that 2D grid. But again, because this is a very unrealistic problem with very unrealistic standards, you're not allowed to just walk this way, right? Like in a normal problem, why can't you just walk from the entrance? But no, you have to do a series of jumps. And the jumps have to be very special. They have to be 2 factors of the previous number. What that means is that if I have this first number is a 6, this means that from 6, I can jump to 1, 6, 2, 3. I can also jump to 3, 2. This is very, very bad. All right. 2, 3.
You're not sharing your
Oh,
screen.
I'm not. Am I not sharing? Oh my God. Sorry.
Mega brain.
So smart. So smart. All right. Okay. I should also share the problem. See, as you can see, I'm very smart. Sorry, my bad. All right. Here's the problem. At least you guys are paying attention. Thank you. All right. So based from this problem, you're given a 2D grid, and you're essentially trying to, go from the top left to the bottom right. Right? And in the normal problem, you could just walk all the way, but you actually can't. You have to use manipulation to solve it, which means you have to do it with some sort of walk. And the walk you have to do is that they have to be factors of the previous number, which means that from 6 you can walk to 1 6, you can walk to 2 3, you can walk to 3 2, and you can also walk to 6 1. Notice that this means that I can walk to any two numbers that multiply up to be a factor of that number, and I can walk to any of these different locations and keep on going. All right, that's essentially the problem, and we also walk through a sample case. So we can now look at the algorithm for this. Let's look at, again, a basic algorithm, but again, this is not going to be as basic. This is going to be more of a brute force question. So first of all, I wanted to highlight one thing of this problem. A lot of people, when they saw this, they started crying and they just couldn't do it. Don't look at a problem and just start crying because you can't think of an algorithm, right? Like, you can cry after the content. What you should actually do is look at the subtask, because even if you can't solve a question, you might be able to solve one of the subtasks of that question. Right? This is really important, because if you can get 2 marks, like let's say me and Matthew are doing the same question, and we both don't know how to solve it. But if I can get 3 out of the 15 marks and Matthew can't get any of the 15 marks, I'm going to beat him by a lot. And that's what it takes really in junior and senior to beat someone. It really doesn't take, completely solving a question, because if you can completely solve it, you're probably, too good for that division. But because this is probably like the hardest question on junior, so you're probably not going to be able to solve it completely. But what you can try to do is solve it partially, and that means you're going to be much more ahead than someone else who just looks at the question and doesn't know how to solve it, just sits there for 3 hours, right? Like, even if you come up with a really bad solution that is really slow and just doesn't work, maybe you can pass some of the cases, right? Like, even getting 1 point is better than getting nothing. And let's look at the subtask. For the first point, m equals to 2 and n equals to 2. This is great because I can legitimately do it by hand, right? Because let's look at this. Because there are only 4 things, I can look at this one, and I can say from this guy, where can I jump to? Can I jump to this guy? And then from here, I can jump to here, here, and here, right? So from 1, I can jump to 2, 3, and 4. And from 2, maybe I can jump to 3 and 4. From 3, I need to check this, right? So from 3, can I jump to 4? And then from 4, can I jump to, nothing? But then 3, I can also jump to 2 and 4. And then you also notice that this defines some sort of recursive property. You need to notice 2 things from the sample case that we did with the 2x2. First of all, this problem doesn't even require recursion, because 2x2 is easy enough that you can just brute force it. So you don't really need any recursion to solve it. But the other thing you need to see is that this is a recursive property, because from 1 I can go to 2 3 4, from 2 I can go to 3 and 4, from 3 I can go to 2 and 4. So this is a recursive property that we're seeing, right? And again, from both of these J5 problems, we see that they're recursion problems. Now let me show you something. I wanted to show you this. It's important. See, J5. I'm going to show you all the J5s from previous years. We're going to sort by year, and we're just, why is this? This sucks. This sucks. Why can't I see them in order? Oh my God, this. Okay, you know what? Category CCC. We're gonna sort by this. Sorry, this sucks. We need to sort by CCC, and we're going to go to J5. If this doesn't let me see J5, I'm gonna cry.
This problem search J5.
You're not searching J5 right now, Mega Brain.
What do you mean? I'm searching J5.
It's S2.
Oh, now you are.
They put it as S2.
Oh, some of them are put it S2. All right.
Yeah.
True.
Damn it. All right.
S5.
Bro, okay. So what I'm trying to say, why are all these S5 J2s? All right. If you look at previous years, like 16, 17, 18, and 19, a lot of these problem J2s or J5s or S2s, a lot of them are recursion-based problems. They're recursion-based problems, like choose your own path, recursion, rule of 3, recursion, pi day, recursion. All these problems are recursion, escape room, recursion. And from these, you can see that a lot of these problems are based on this property. And then from this property, we're going to see that, so next time when you see a CC problem, you're going to immediately think recursion, right? Because you're going to see it and you're going to say, oh, most of the problems from previous years were recursion, so this problem is recursion. It's just something you can do. But even if you don't, you need to be able to realize recursive properties. This is important for you because almost all CCCs have some sort of recursive problem. Now, you see that recursive problem and you think, how do I solve it? right? Because obviously you want to solve it. Escape room. Let me go back to the question. This is escape room hard, not escape room. So from here, we're going to look at the next one, which is all the cells are unique and for the next one. So for our recursive property, what we're going to do now is that we're going to see from one square, we're going to go to all squares with a factor of that number in it, right? So let's say that we're from 6. From 6, we're going to go to 1, 6. We're going to go to 2, 3. And then we're going to go to 3, 2. And we're going to go to 6, 1. And that's going to be our base of recursion. And we're going to keep branching down. Now, there are two problems with this. First of all, there are going to be loops and you're just going to be doing it forever, right? Like let's say I go to 6 and then I go to 1, 6. And then I see that 1, 6 has 1 and then I go to 1, 1. I'm just going to keep going forever and that's not good. Right, so first of all, we have infinite loops. Second of all, we notice that this is very slow because again, because it branches. Always remember that because it branches, it's going to have a time complexity of O2 to the n because at each step, you're going to have at least 2 branches to go to. So it's going to be too slow to solve any of these subtasks because you have 1,000, 1,000. Don't even think about doing it. So how do we fix the problem? Now, this is actually very similar to the previous one because we can use a visited array. Notice that if I have 2 paths, I can actually model this as a graph, but it's not the intuitive way of modeling it. It is actually modeled as a 2D graph because if I notice that if I have 2 paths to reach the same point, right? I have 2 paths to reach the same point, but one of these paths take a shorter distance, I'm not going to take it. Remember, if one person has to go around the world and the other person has to go to their neighbor, you're going to tell the person who's going around the world to just stop because they don't need to go that length. And which means that this line will be cut, which means that we will shorten the solution by a lot. And also notice that because I have a visit array, I know when one has been visited before, so I'm never going to visit a node another time. When I if I visit one node more than once, I'm just going to cut it, right? Because I don't need to go there. And what I do is I'm going to use a distance array, but again, this is going to be modeled as a graph. Remember what we did when we had a graph. We had sort of like a 1D array, right? We had this, and we had 1D arrays, right? 2 1D array. This is visit, this is distance. We don't need that for this problem because for this problem, we need everything is 2D. So we're going to have a 2D. This is going to be 2D. We're going to have a distance array, which is 2D. And in fact, this method is legitimately called 2D BFS. I'm not joking. That's what it's called. It's so simple that it's the same thing as BFS. It's just 2D BFS, right? We loop to each point and we see if it's been reached. Again, the important thing is we transform the problem into a graphical one. We notice that we can run BFS on the graph, and we can use distance arrays to shorten that recursion that we make. Now, the final thing is we need to analyze the time complexity here, and this is what makes the problem really hard. This is what takes you past J. This is what gets you to J1 perfect score, and this is junior perfect score, and this is what really, really makes you a good programmer. Notice that the time complexity is very long. Now, I think Martin actually did this solution, but Martin missed one crucial error is that he didn't analyze the time complexity of his solution. What is the time complexity of the solution? Notice that I actually have to spend O, N, M, right? Because I need to go to each array element once. But from each element, I have at most n factors of that number, right? Because remember, each one still has a branch n times, right? And if we simplify that, we have O, n squared m. And that is too slow to pass, right? So instead of just trying random cases, maybe think about your time complexity and realize that this is too slow. How? Yes, 11 out of 15, but that is already very good. How do we improve this algorithm? I'm going to show you 2 ways to improve it further and further. First way, I'm going to notice that because this is n squared m, I want to take out the n factor. How do I take out the n factor? Well, no, this is when we use math. Notice that I have n equals to a times b. If I have 2 numbers and multiply to n, I have a is less than square root n. I always have that. Why? Because notice that n is equal to square root n times square root n. This is a radical. If we write it in radical form, we see that if 2 numbers multiply out to n, one of them must be less than, a must be less than equal to square root n, and b must be greater equal to square root n. This means that if we want to find all the factors of n, we only need to search for a. If we find a, b, we immediately flip the 2 numbers and we find b, a. this does not take half the time. A lot of people make the mistake to think that this makes half the time. If this takes half the time it used to, it's not an asymptotic improvement. But this takes faster time because you realize that you only have to loop to square root n, and this is so much faster. Now you get O, time complexity of O, and M, square root n. Square root, actually this is not n, this is actually square root t, the total amount of each number. So this is actually O n t m, right? And then finally we realize that this is O n square root t, right? But then, oh, I can just write it like this. But then also notice that OM square root t is 10 to the 9. This will pass on CCC grader, but unfortunately, this will not pass on DMOJ. Because again, the DMOJ admins are very mean and they don't want you to pass. So what do we do? And what do we do if we're faced with this question during a contest and we don't know what to do? It's actually really simple. We keep simplifying. We keep optimizing. We're going to optimize one more time, and then that's going to be the answer. Don't worry. It's not going to be that long. Last optimization. We're going to realize that because we have square root t, we want it to become 1. This means that we can do 3 different optimizations. We can, 1, pre-compute all the factors. What does that mean? That means that if I know all the factors of 6, so 1, 2, 3, 6, I can do this in O1 time, which makes the complexity ONM, because the t disappears because I know already all the factors. I had to calculate the factor in square root n, but if I can do it pre-processed, then it's going to be ONM plus square root t. This is really important. This is actually a computer science concept. It requires the use of math, but also you need to learn that this is called pre-computation. Pre-computation query time. Pre-computation versus query time, yes. What that means is that if I split the time needed in a query and I move it over to pre-computation, both numbers will be added up instead of multiplied, right? The pre-computation solving save time means that instead of doing everything at once, I split it into 2 and I add it together and the number becomes less. The second way I can do it, if you don't understand this, is completely fine. You just pre-compute the factors and numbers become smaller. You need to know some math to do this because you need to understand why I want to split it and not multiply. The other way I can do it is using a ADJ list, adjacency list. Okay, that is going to end in 3 seconds, but that's fine. You're going to use an ADJ list to do it. And the last time is called a reverse sweep. And what that does is that you're going to sweep through every other value in the array, and then you're going to work backwards. This makes it so much faster because you don't have to pre-compute any factors. That's the problem. Yeah. You guys, any questions?
Okay. I think I'm just gonna go really quickly through S1.
Sorry that took too long.
It's all right. Okay, so this is S1. So if you did the senior, right, this is S1. So if you get this question right, you should be able to get this question if you're doing senior, or else you wouldn't get much points out of the CCC. Okay, so Tricky Dingo is trying as usual to catch his nemesis, the street sprinter. His past attempts using magnets, traps, and explosives has failed miserably, so he's catching his breath to gather observational data and learn about how fast street sprinter is. Okay, this is just like garbage text, just like what Jerry said.
What is Tricky Dingo's
Tricky
middle name?
Dingo.
What is Tricky Dingo's middle name? It's an initial. It's E.
Yeah, well, I don't know. Tricky Dingo?
Yeah,
I
what's
think a
his,
dingo is the kind of animal.
his middle name is only an initial, so what is it?
Yeah, well, it won't help you solve the problem, so we're just going to ignore that. Unless it haunts you for the rest of the contest, which is bad. Tricky Dingo.
It might will. It might.
Yeah, so they inhabit a single straight west-east road with a particular famous rock on it known as their origin. Positions on the straight road are measured numerically according to the distance from the origin, using negative numbers for positions west of the origin and positive numbers for positions east of the origin. So this sounds like a number line, right? If you're on a number line, you have an origin, which is 0, right? And then you get negative numbers if you're left of it, and you get positive numbers if you're right of it. So just think of a number line when you see this problem. So the observations by Tricky Dingo each contain two numbers, a time and the value of street sprinter's position on the road at that time. Given this information, what speed must street sprinter be capable of? Right. And then now we have to take a look at the input specification. So the first line contains a number, which is the number of observations that follow. So you know that you're going to get 100,000 points. And that's a really big number. And we'll explain the significance of this later on, right? And that each line contains an integer, which indicates the time in seconds of when a measurement is made, and the integer including the position of the street sprinter at that time. No two lines will have the same value of t. And then you want to output what is the maximum of street sprinter's speed, right? You want to find what is his maximum speed at any point when street sprinter is running. So that's basically what you have to figure out. Well, let's look at how we can solve this problem. Well, I already mentioned the number line, and that should come to mind pretty easily. Let's take a look at the solution. So let's plot it out in a number line. So here, the number line, the axis is t, so this is time, right? So at time 0, I asked the street sprinter, where are you at? Well, street sprinter is at 100. At t equals 10, so at 10 seconds, he's at 120 meters. And at 20 seconds, he's at 50 meters, right? So basically what I did is I just sorted the points by time, right? In a number line like this, I'm just sorting the points by time, and you get this kind of ordering, right? So what is the naive solution? Well, let's not even think about the number line. Let's just calculate the speed between any 2 points on the line, right? So what can we do? Well, we can do nested for loops. We just find the distance between every pair of points and just use a for loop to calculate that. And we know that how do we find speed again? Those of you who have taken physics or at least some sort of math. If I have position 1 and I have position 2, I have time 1 and time 2. Well, what's the speed? Does anyone know? What's the formula? Does anyone know? What's the formula for speed? Change in what over change in what?
Maybe I'll help you out.
Distance over time. Okay, great. So change in distance or change in time. This is what you probably learned this in math before, right? So if I have x1, s2, t1, t2, then s is equal to t2 minus t1, x2 minus x1. Yeah. So this is basically the formula for calculating speed. If you don't know this formula, you better memorize it now, because if you didn't know this formula, you wouldn't be able to solve this question, basically. So what do? I just apply this formula with every combination of points, right? I'm like 0.1, 0.2, what is the speed between these 2 points, right? And then I take the maximum of that. And then max would give me the answer, right? I just take the maximum of like the distances between every pair of points. This is not going to give you the full amount of points because it takes n times n time. So how do we know it's n times n? Where how many times does the outer for loop run? N times, right? The number of points. And how much times does the inner for loop run? Well, it runs n times. So every single time the outer for loop runs, the inner for loop runs n times. So the time is n times n. And what is n? N is 100,000. So you got 100,000 times 100,000. This for loop is going to run like, what, 10 to the 10, like around that number of times, right? Whoa, it actually calculates it for me. And that is go to TLE. It's going to run out of time. But this will get you partial marks though, right? So you should, if you don't know the best formula, just write a very naive solution. Just calculate the distance between every single pair of points. And you don't need to sort anything for this. And you'll probably get like 4 points for that. Well, let's take a look at the efficient solution, right? If I sort my points like this by increasing time, so I have an object I have an object. Okay. This is called a point. Okay. Excuse my drawing skills. And what is a point? Well, a point has a position, right? It has a position equals something. And it has a time, right? So this is an observation, basically. So a point has a position and a time. And how do we sort it? Well, we can sort it based on time, right? And then we'll get this number line. So we can do that. We can sort that. And you know how to use comparators if you are in CP Java. You know how to sort by time. And point is just an object. And you sort it by time using comparators. Well, after we sort it, we only have to calculate the distance between every pair of adjacent points. I calculate what's the distance, what's the speed between here, and what's the speed between here, right? So here, the difference is 20. 20 divided by 10, well, this is 2 meters per second, right? We're just using the plain old formula here. Between 10 and 20, it's 70, right? This is the difference divided by 10. That's just 7 meters per second. I hope I'm calculating it right. So what's the fastest speed it can go? Well, the fastest speed it can go is 7 meters per second. So we just take the maximum of all the speeds that we calculate between every pair of adjacent points. So how do we know this is true? How do I know that the speed between here and here is not faster than the speed between here and here, and the speed between here and here? Well, we can observe that the speed between 0 and 20, the average speed, cannot exceed the speed between 0 and 10 or 10 to 20. One of these is going to be the maximum, right? The average of all the speeds cannot be greater than the speed at any point of time, right? So therefore, you just take the maximum of all the speeds you calculate between adjacent pairs. So I'm just going to show you the solution that I got. So I created a pair object, right? This is a point. It has a time, it has a position, which I call D, right? And we use comparators to sort it by time. Well, we just create a new pair, right? When we're reading it in, and we sort those pairs, which would sort them by the time, right? And then I just calculate the speed between every adjacent pair, right? And then I find the maximum, and I just print out the maximum. So the code's actually super, super simple. You just needed to understand that you need to sort all of the observations, and you just find the speed between every adjacent pair of observations. Yeah, so hope you guys got that. Do you guys have any questions about it? No? Okay, I guess that's the end of today's lesson. Yay.
Yeah.
It's a very long lesson.
We did a lot of teaching. We solved a lot of problems. If you have any problems with any of them, you can contact any of us on the Discord.
Why do Java programmers always have to have classes for everything?
Yes.
It runs within the class. That's how Java works.
Yes, that's a reason you don't use Java, because too many classes.
Bruh.
Yes.
Java getting low-key bullied right now.
Yes, because it's slow. Well,
HTML best language.
Bro, if you use HTML, I'm gonna be like, how?
Oh,
Greenfoot's better.
Maybe I should.
Worse.
I should show you guys how to round integers and stuff. I forgot to teach that.
Do you want to do that now?
Okay, let's do that now.
Okie dokie.
I think someone asked me this earlier. Okay, so I'm going to screen share. If you already know how to round integers and stuff, you can feel free to leave. But I'm just going to go over some some stuff because if you don't know how to round, then that becomes a problem, right? Because even if you come up with the correct answer, you can't output it well. Okay, Replic's just broken at the moment, I guess. Okay, let's say I have a double. Okay, a double is just a number with I don't know, that's the decimal points, right? I have a number like 3.1415926535897932338. Okay, don't ask me how I remember all the digits of pi, right? And let's say I wanted to round this integer to the closest one digit, right?
Minor mega flex.
Mega flex. Damn, dude.
So I wanted to round to 3.1, right? Because when we're rounding, we look at the 4, right? The second digit, and we're like, oh, 4 is closer to 0 than to like the next, like 3.2, right? 3.14 is closer to 3.1 than 3.2. So what do we do? Well, it becomes 3.1 then, right? Well, how do we tell the computer to do that? Well, the easiest way is to do something like this. So let's just print this out. I'll explain why it works in a moment. Let's see if that works. Replit is very slow. 3.1, okay. So this is how you can round to the closest one digit. Well, how does it work? You might say. So let's see what d times 10 becomes. Well, d times 10 becomes 31.415 blah 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 blah, right? Let's zoom in. D times 10 becomes 31.415 blah 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 blah. And then what do we do with the 4? Well, we want to round it off, right? So what does math.round do? Math.round rounds to the nearest integer. So it looks at the 4 and it's like, well, the 4 makes it closer to 31 than 32, right? So then math.round d times 10 would just be 31, right? And what do we do? Well, we divide it by 10 again, right? But we're making sure it's a double now, right? And then we'll end up with 3.1. So this is how you can round numbers in Java. We can test it out. Let's change this to a 5. Well, this should round to 3.2, right? A 3.2, see? Okay, so this rounding works, right? If you want to round to the closest one digit, multiply by 10, round it, so you strip off all of the other digits and round that to the closest integer, and you divide it again. So you're like, multiply by 10 and divide by 10, don't you get the same number? Well, no, because you rounded off the rest of the digits. Well, how do I round to the closest 2 digits, right? Closest 2 digits. So if I did 3.1415, then it would be 3.14. Well, let's use a similar pattern. It'll just be math.round d times 100, right? Because we're shifting it 2 to the left now, divided by 100.0. And then this would just give you your closest 2 digits. And then we can do the same analysis. D times 100 equals 314.15926, right? Math.round of that, d times 100 gives you 314. And then you divide it again. D divided by 110 equals 3.14. So you're shifting it over and you're calling the round function to round off the rest of the digits after the decimal, and then you divide it again. So 1 digit would be 10 to, you would just times 10 to the 1, right? 2 digits, you would multiply by 10 to the 2. If you want to round it off to the closest 3 digits, it will be 10 to the 3, right? So system.out.println math.round d times 1,000 divided by 1,000. And then this would give you your closest 3 digits. right? You're rounding to 3 digits. Well, you might ask, well, what if the problem doesn't say round? It just says strip off the rest of the numbers, right? So it might say output to 2 decimal places. And what that basically means is if I have a number like 3.1415, how about 3.15, right? And I want you to output to 1 decimal place. I just want 3.1, right? If it's 3.16, I want you to output 3.1. If it's 3.17, I want you to output 3.1. So like anything, just output the first digit. What do? Well, in Java, you have a class called decimal format, text.decimal format. So this is actually relevant in the Vonaroy villages problem that was shown to you earlier by Jake, because you need to output to 2 decimal places, right? So if I want to output to 1 decimal place, I'll do 0.0. And all I have to do is system.out.println df.format d. And that'll just give you it to 1 decimal place. If you want 2 decimal places, well, df new decimal format 0.00. And this will give you to 2 decimal places. It'll just strip off everything that comes after the 2 decimal places. So that's how you can chop off digits. And this is how you can round. So does everyone understand how to output to x decimal places and how to round to x decimal places? Make sure you really understand this. Or else when you might come up with the right answer, but the program is going to say you're wrong because they want you to output it in a certain format.
Yes. And yes, that's a very important method that I guess Grinder showed you.
In my code, I used a string format, just saying.
And if you are planning on using C++, it is the cout has a function which is called set precision, where you can do this a similar thing where you can just chop off different digits, and then rounding you just use a similar method to in Java for rounding.
Yeah.
Silence.
Does anyone have any questions? Any final questions? This is the last meeting before the CC.
Yeah, so we try and tell you as much as we can before to get you prepared.
Thinking of some other things that you should keep in mind. Oh, make sure to practice using the CCC grader. Like know how you can download your Java code as a zip and then you upload it to the CCC grader.
Also,
you can if you can, you can copy and paste your Java code into Notepad and just submit the Notepad as a .txt file. That also works.
I mean, you could do that, but I don't think that's a good idea. Also, if you're like using Java or something, figure out how to use the fast buffer reader before you do the contest.
Oh, yes. Oh, I forgot to talk about that. Okay. Give me a second.
Buffer reader is pretty simple. It's not too hard.
New buffer reader and read line.
Buffer reader is basically, if you know Java, I've been using Scanner for the entire time because Scanner is really easy to read in integers, read in strings, right? But then it's not the fastest. Like there's a way that's like 400 times faster to read in stuff. It shouldn't matter if you're writing junior, but if you're writing senior, it might have an effect on how many marks you can get. Just give me a second. I need to go find where I have.
I would recommend a buffered reader if the J5 has like a long input. I would recommend using buffer reader there.
Yeah, I'm gonna paste in this thing so you guys can copy it down. Okay, I got the link. I'm gonna put it in the chat. You guys can copy this into your code. It looks very complicated, but it's very easy to use. I'll demonstrate how to use this template, okay?
I mean, well, for Martin, I mean, if you pass all test cases, it It means your program's already fast enough, but there are certain times when you're doing a program, it's not, you need to make it go faster. So you use something like buffer reader to make it go faster so it can pass more test cases or even all of the test cases.
Yeah, so I'm gonna share my screen. Okay. Okay, so I just basically paste my paste the template into here. So this is what you get with when you start off, right? So now I don't have scanner. You're like, how do I read integers and stuff? Like, this is so confusing. Well, fear no more. All of the methods are down here. If I want an integer, I can just do int a equals readInt. I just call that method. And readInt would just handle reading integers. Well, how do I read another integer? Well, I'll just do readInt again, and then I can print out a plus b. So done. You've already solved the problem with fast input-output.
Yes.
Right?
I mean, yeah, you can just literally straight up copy paste it. I mean,
yeah.
It's not against the rules or anything.
Oh wait, you should remove this BIT thing. I forgot to remove it. Whoops. Okay, yeah, you should remove that array thing. That's not necessary. Okay. I was just solving another problem and then I still had that array there. So this is how you can read integers. If you want to read string, you can do string s.next. Next only takes the entire word. So if I have a string, I'm reading like hello world, s will only give me hello. So next just takes a word, right, all the way up to the white space. Read line would give me the entire line. So if someone input hello world, then s would be hello world. Yeah. So this is fast input output. Your reading in integers and outputting integers is going to be 400 times faster if you use this.
Yeah, it's a lot faster.
A lot faster. Right? It doesn't matter for junior because all the constraints are very low. But once you get to senior and you see numbers like you're reading in 100,000 integers, then speed matters, right? So just use this template and remove that array thing that I had there. That was unintentional. So yeah, practice using this template. Don't use scanner, use these methods. Anyone have any questions? So we've gone over input output. We've gone over how to format decimal places, how to round. Yeah, technically no starter code. I mean, you can memorize it. But I don't think it's that big of a deal, honestly.
Honestly, you don't really need all those helper methods. Those are basically just like taking buffered reading and turning it into a scanner type thing.
Yeah. Oh, also another thing is there's a contest going on. You guys should definitely try it. It's also very beginner oriented. It's called Applebee contest. They said it's like CCC J1 to CCC S3. We took out J3 to S2 problems today. So if you're comfortable with that, you should do the Applebee contest. You have nothing to lose. Like you don't even lose rating if you're caring about rating because it's unrated. And let's see who's doing well. Well, you know, like a lot of people got perfect on this contest. So you should definitely just try it out. It's good practice. Oh, there's also another mock CCC coming out tomorrow.
Oh yeah,
Yeah.
Bioklu or whoever that is.
Yeah. Any questions? If you don't have any questions, you can feel free to leave.
So I think that's it for today's lesson.
Yeah.
Right? Yeah. So good luck on the CCC when next time we see you.
Yeah, good luck. Wait, how is it 5? What do you mean?
What does it 5 mean?
Was it 5 o'clock? Yeah.
Oh yes.
That was fast. Time
It took
goes
a long
fast.
time.
Time passes fast when you're having fun.
Yeah.
So
If
funny.
you found the graph theory things confusing, you can search up graph theory and you learn a little bit more. If you're doing senior, you're likely to come into graph theory problems, at least one every single year. So make sure to learn it. I think you can learn it on Hacker Earth. Hacker Earth also teaches you about graphs, which is what Jerry was talking about. So if you didn't understand what Jerry was talking about, learn graph theory. Right, so these were like the things that he was drawing earlier. So you can learn this, right? Adjacency lists, he was talking about adjacency lists, right? How do we store these kinds of structures, right? So just learn it somewhere. Like Hacker Earth is a good place. YouTube is a good place.
I mean, YouTube is not such a good place.
It depends what you do. Yeah.
You just
If
gotta
have
find the good videos.
Those are hard.
Yeah, if you have no questions, you can feel free to leave. But good luck on your CCC.
Good luck on the CCC. See you guys.
Yes. See you guys next time.
Oh, Ryan, I think you can stop recording now.
Oh yeah. Wait, stop sharing stuff.